Xenon is a chemical element with symbol Xe and atomic number 54. It is a colorless, dense, odorless noble gas that occurs in the Earth's atmosphere in trace amounts. Although generally unreactive, xenon can undergo a few chemical reactions such as the formation of xenon hexafluoroplatinate, the first noble gas compound to be synthesized. Naturally occurring xenon consists of 8 stable isotopes. There are also over 40 unstable isotopes that undergo radioactive decay. The isotope ratios of xenon are an important tool for studying the early history of the solar system. Radioactive xenon-135 is produced by beta decay from iodine-135, and it acts as the most significant neutron absorber in nuclear reactors. Xenon is used in flash lamps and arc lamps, and as a general anesthetic. The first excimer laser design used a xenon dimer molecule as its lasing medium, and the earliest laser designs used xenon flash lamps as pumps. Xenon is also being used to search for hypothetical weakly interacting massive particles and as the propellant for ion thrusters in spacecraft. History. Xenon was discovered in England by the Scottish chemist William Ramsay and English chemist Maurice Travers in September 1898. Shortly after their discovery of the elements krypton and neon, they found xenon in the residue left over from evaporating components of liquid air. Ramsay suggested the name xenon for this gas from the Greek word Xi epsilon nu omicron nu, xenon, nu to singular form of Xi epsilon nu omicron sigma, xenos, meaning foreign, strange, or guest. In 1902, Ramsay estimated the proportion of xenon in the Earth's atmosphere as 1 part in 20 million. During the 1930s, American engineer Harold Edgerton began exploring strobe light technology for high-speed photography. This led him to the invention of the xenon flash lamp, in which light is generated by sending a brief electric current through a tube filled with xenon gas. In 1934, Edgerton was able to generate flashes as brief as 1 microsecond with this method. In 1939, American physician Albert R. Benker, Jr. began exploring the causes of drunkenness in deep-sea divers. He tested the effects of varying the breathing mixtures on his subjects, and discovered that this caused the divers to perceive a change in depth. From his results, he deduced that xenon gas could serve as an anesthetic, although Russian toxicologist Nikolai V. Lazarev apparently studied xenon anesthesia in 1941. The first published report confirming xenon anesthesia was in 1946 by American medical researcher John H. Lawrence, who experimented on mice. Xenon was first used as a surgical anesthetic in 1951 by American anesthesiologist Stuart C. Cullen, who successfully operated on 2 patients. Xenon and the other noble gases were for a long time considered to be completely chemically inert and not able to form compounds. However, while teaching at the University of British Columbia, Neil Bartlett discovered that the gas platinum hexafluoride was a powerful oxidizing agent that could oxidize oxygen gas to form dioxygenol hexafluoroplatinate. On March 23, 1962, he mixed the 2 gases and produced the first known compound of a noble gas, xenon hexafluoroplatinate. Since then, many other xenon compounds have been discovered, along with some compounds of the noble gases argon, krypton, and radon, including argon fluorohydride, krypton difluoride, and radon fluoride. By 1971, more than 80 xenon compounds were known. In November 1999, IBM scientists demonstrated a technology capable of manipulating individual atoms. The program, called IBM in Atoms, used a scanning tunneling microscope to arrange 35 individual xenon atoms on a substrate of chilled crystal of nickel to spell out the 3-letter company acronym. It was the first time atoms had been precisely positioned on a flat surface. Characteristics: xenon has atomic number 54, that is, its nucleus contains 54 protons. At standard temperature and pressure, pure xenon gas has a density of 5.761 kilograms per cubic meter, about 4.5 times the surface density of the Earth's atmosphere. 1.217 kilograms per cubic meter. As a liquid, xenon has a density of up to 3.100 grams ml, with the density maximum occurring at the triple point. Notably, liquid xenon has a high polarizability due to its large atomic volume, and thus is an excellent solvent. It can dissolve hydrocarbons, biological molecules, and even water. Under the same conditions, the density of solid xenon, 3.640 grams per cc, is higher than the average density of granite, 2.75 grams per cc. Using gigapascals of pressure, xenon has been forced into a metallic phase. Solid xenon changes from face-centered cubic to hexagonal close-packed crystal phase under pressure and begins to turn metallic at about 140 gigapascals, with no noticeable volume change in the HCPE phase. It is completely metallic at 155 gigapascals. When metallized, xenon looks sky blue because it absorbs red light and transmits other visible frequencies. Such behavior is unusual for a metal and is explained by the relatively small widths of the electron bands in metallic xenon. Liquid or solid xenon nanoparticles can be formed at room temperature by implanting Xe+ ions into a solid matrix. Many solids have lattice constants smaller than solid Xe. This results in compression of the implanted Xe to pressures that may be sufficient for its liquefaction or solidification. Xenon is a member of the zero-valence elements that are called noble or inert gases. It is inert to most common chemical reactions because the outer valence shell contains 8 electrons. This produces a stable, minimum energy configuration in which the outer electrons are tightly bound. In a gas-filled tube, xenon emits a blue or lavenderish glow when the gas is excited by electrical discharge. Xenon emits a band of emission lines that span the visual spectrum, but the most intense lines occur in the region of blue light, which produces the coloration. Occurrence and production. Xenon is a trace gas in Earth's atmosphere, occurring at 87 plus or minus 1 parts per billion, or approximately 1 part per 11.5 million, and is also found as a component in gases emitted from some mineral springs. Xenon is obtained commercially as a byproduct of the separation of air into oxygen and nitrogen. After this separation, generally performed by fractional distillation in a double-column plant, the liquid oxygen produced will contain small quantities of krypton and xenon. By additional fractional distillation steps, the liquid oxygen may be enriched to contain 0.1–0.2% of a krypton-xenon mixture, which is extracted either via absorption onto silica gel or by distillation. Finally, the krypton-xenon mixture may be separated into krypton and xenon via distillation. Worldwide production of xenon in 1998 was estimated at 5,000 to 7,000 cubic meters. Because of its low abundance, xenon is much more expensive than the lighter noble gases. Approximate prices for the purchase of small quantities in Europe in 1999 were €10 per L for xenon, €1 per L for krypton, and 20 cents per L for neon. The much more plentiful argon costs less than a cent per liter. Within the Solar System, the nucleon fraction of xenon is 1.56 times 10⁻⁸, for an abundance of approximately 1 part in 630,000 of the total mass. Xenon is relatively rare in the Sun's atmosphere, on Earth, and in asteroids and comets. The planet Jupiter has an unusually high abundance of xenon in its atmosphere, about 2.6 times as much as the Sun. This high abundance remains unexplained and may have been caused by an early and rapid buildup of planetesimals, small, subplanetary bodies, before the pre-solar disk began to heat up. The problem of the low terrestrial xenon may potentially be explained by covalent bonding of xenon to oxygen within quartz. hence reducing the outgassing of xenon into the atmosphere. Unlike the lower-mass noble gases, the normal stellar nucleosynthesis process inside a star does not form xenon. Elements more massive than iron 56 have a net energy cost to produce through fusion, so there is no energy gain for a star when creating xenon. Instead, xenon is formed during supernova explosions by the slow neutron capture process of red giant stars that have exhausted the hydrogen at their cores and entered the asymptotic giant branch. In classical nova explosions and from the radioactive decay of elements such as iodine, uranium and plutonium, isotopes and isotopic studies, naturally occurring xenon is made of 8 stable isotopes, the most of any element with the exception of tin, which has 10. Xenon and tin are the only elements to have more than 7 stable isotopes. The isotopes 124Xc and 134Xe are predicted to undergo double beta decay, but this has never been observed, so they are considered to be stable. Besides these stable forms, there are over 40 unstable isotopes that have been studied. The longest-lived of these isotopes is 136Xc, which has been observed to undergo double beta decay with a half-life of 2.11 x 1021 year. 129Xe is produced by beta decay of 129I, which has a half-life of 16 million years, while 131MXe, 133Xe, 133MXe, and 135Xe are some of the fission products of both 235U and 239Pu, and therefore used as indicators of nuclear explosions. Nuclei of 2 of the stable isotopes of xenon, 129Xc and 131Xc, have non-zero intrinsic angular momenta. The nuclear spins can be aligned beyond ordinary polarization levels by means of circularly polarized light and rubidium vapor. The resulting spin polarization of xenon nuclei can surpass 50% of its maximum possible value, greatly exceeding the thermal equilibrium value dictated by paramagnetic statistics. Such non-equilibrium alignment of spins is a temporary condition, and is called hyperpolarization. The process of hyperpolarizing the xenon is called optical pumping. Because a 129Xe nucleus has a spin of 1/2, and therefore a zero electric quadrupole moment, the 129Xe nucleus does not experience any quadrupolar interactions during collisions with other atoms, and thus its hyperpolarization can be maintained for long periods of time even after the laser beam has been turned off and the alkali vapor removed by condensation on a room temperature surface. Spin polarization of 129Xe can persist from several seconds for xenon atoms dissolved in blood to several hours in the gas phase and several days in deeply frozen solid xenon. Some radioactive isotopes of xenon, for example, 133Xe and 135Xe, are produced by neutron irradiation of fissionable material within nuclear reactors. 135Xe is of considerable significance in the operation of nuclear fission reactors. 135Xe has a huge cross-section for thermal neutrons, 2.6 times 106 barns, so it acts as a neutron absorber or poison that can slow or stop the chain reaction after a period of operation. This was discovered in the earliest nuclear reactors built by the American Manhattan Project for plutonium production. Fortunately, the designers had made provisions in the design to increase the reactor's reactivity. 135Xe reactor poisoning played a major role in the Chernobyl disaster. A shutdown or decrease of power of a reactor can result in buildup of 135Xe and getting the reactor into the iodine pit. Under adverse conditions, relatively high concentrations of radioactive xenon isotopes may be found emanating from nuclear reactors due to the release of fission products from cracked fuel rods, or fissioning of uranium in cooling water. because xenon is a tracer for two parent isotopes. Xenon isotope ratios in meteorites are a powerful tool for studying the formation of the Solar System. The iodine-xenon method of dating gives the time elapsed between nucleosynthesis and the condensation of a solid object from the solar nebula. In 1960, physicist John H. Reynolds discovered that certain meteorites contained an isotopic anomaly in the form of an overabundance of xenon-129. He inferred that this was a decay product of radioactive iodine-129. The isotope is produced slowly by cosmic ray spallation and nuclear fission, but is produced in quantity only in supernova explosions. As the half-life of 129I is comparatively short on a cosmological timescale, only 16 million years, this demonstrated that only a short time had passed between the supernova and the time the meteorites had solidified and trapped the 129I. These two events were inferred to have happened during the early history of the Solar System, as the 129I isotope was likely generated before the Solar System was formed, but not long before, and seeded the solar gas cloud with isotopes from a second source. This supernova source may also have caused collapse of the solar gas cloud. In a similar way, xenon isotopic ratios such as 129Xe, 130Xe and 136Xe, 130Xe are also a powerful tool for understanding planetary differentiation and early outgassing. For example, the atmosphere of Mars shows a xenon abundance similar to that of Earth. 0.08 parts per million. However, Mars shows a higher proportion of 129Xe than the Earth or the Sun. As this isotope is generated by radioactive decay, the result may indicate that Mars lost most of its primordial atmosphere, possibly within the first 100 million years after the planet was formed. In another example, excess 129Xe found in carbon dioxide well gases from New Mexico was believed to be from the decay of mantle-derived gases soon after Earth's formation.